Hi. I'm really honored and also a little bit nervous to be here because there's such a big, great gathering here. My name is Ashwin, and I run a company called Proto Central in India. We're based in Bangalore. What we do is we make open source hardware specifically for medical devices, and we also sell a bunch of cool open source hardware from all our partners. So I'm going to be talking about a cycle that is going on within me and how I first fell in love with open source hardware, when I first got to meet open source hardware, how we used them later in medical devices and medical research projects that we are working on, and how we used it even more, and now how we are contributing back to the open source hardware field. So this is how this was my first open source project that I've seen. It was called OpenEEG. This was back in 2001, and at that time OpenBCI was not around, and and EEG was still new, and it was very difficult to do. So we got started with this project where we wanted to make a wireless EEG headset using Bluetooth, but the problem was both EEG and Bluetooth were difficult for us because of the limited resources that we had. I was my first year of college. But this website really helped us. I mean, OpenBCI, they gave us the schematics for a basic EEG amplifier and how to hook it up to electrodes and then the rest of the things. So you can see a pretty, I think it's a pretty bad picture of a board that we made. That was the initial board that we made, and since we didn't have resources or money to buy boards from OpenEEG, we made our own board. That board that you see there is the EEG 6-channel EEG amplifier, and I didn't have access to Eagle even at that point. So, you wouldn't believe that I actually drew the PCB out on Microsoft Paint and then etched it out of copper. And the really ugly looking box that you see on top is our enclosure, if you can call it that. So what I mean by the second arrow here is that this started my journey in open source hardware. It also got me into biomedical instrumentation. At that time I was doing my college in software engineering, which was completely different from biomedical engineering. But finally I got into biomedical engineering, and that led to even my thesis was on wireless EEG, and it was received quite well at the time. So the next thing I'm going to be talking about is, we are working on a lot of projects which use open source hardware in various fields, but today's talk is going to be on medical devices. So I'm going to be talking about two projects that are the most recent. We worked on a number of them, more than 10 of them, but two of them which are more recent and which are more meaningful. So I apologize if anybody is grossed out with the video here. So what we've done is pancreatic cancer. I think everybody knows pancreatic cancer is a very common form of cancer, and I think pancreatic cancer got popular because Stephen Jay died of it, and everybody got to know what pancreatic cancer was. The operation for pancreatic cancer is called Whipple's procedure, and what it involves is resectioning, or just put it in crude words, cutting off the part of the pancreas that is cancerous, and then tying the pancreas. The pancreas is filled with an amylase fluid. So when you cut off a part of the pancreas, then the fluid starts leaking. So it's sutured back to the stomach or the intestine so that the fluid doesn't leak. And I've got a quick video here, which shows it's not too clear. I'm sorry, I can share the video with you if anyone's interested. What it shows is the doctors suturing the pancreas back to the. It looks pretty crude, but that's how the Whipple's procedure is done. And we've been lucky to have partnered with Dr. Ravichandran from Stanley Medical College in Madras in India, who is one of the doctors who is an expert on Whipple's procedure. So the problem here is, as I told you, the fluid leakage happens due to a lot of reasons, but one of the main reasons why this happens is because the knot is not tied properly. And if you want to put it so crudely, it's because of the knot is not tied properly. It's called the ligature force. And let me run this video again. If you see, there are two surgeons. One is putting his hand on the pancreas, and there is another surgeon who is pulling the thread out of the pancreas. So both of those forces are important. There are soft pancreas and there are hard pancreas, so both would require different types of force and all that. So the problem here is, and the mortality and the morbidity of the outcome, that is, to put it in very crude terms, mortality is whether the patient is going to walk out alive of the operation theatre, and morbidity is how long is he going to live for after that. So that directly correlates to the fluid leakage. Now the problem here, that not tying force, what is the perfect force where you can minimize the leakage, is very subjective to the operating surgeon. And there are only a few qualified surgeons in the entire world who can successfully do a Whipple's procedure. And since morbidity depends on that, it dictates the person's lifetime, the life expectancy. So this was the problem with which the doctor came to us, the surgeon, how to get more doctors involved. So what did we do? We tried to quantify the force that is there. So we quantify the force using some sensors in the operating gloves while the doctor is doing the surgery. In real time, it provides feedback to the operating surgeon or surgeons. And we used that data and tried to train more surgeons. All this work was done by the doctor. I mean, usually it's very difficult to get a doctor to work with any experimental devices, but there are some who are really interested in bringing in new methods and all that. So we were lucky to have Dr. Ravichandran from Stanley. So this is how it works. I'm just going to quickly go through it. We have two small force sensors. Those are simple flexi-force sensors that we got from SparkFun, and those are put inside the surgical gloves. And we made an Arduino-based device to digitize that and send it over through Bluetooth. And we made a Raspberry Pi-based display for that. So this was prototype number one. And as all prototype number ones look, it was pretty crude. So the box that you see there, that was our enclosure. It was a Tupperware box that we got and we put it inside it. It was for a couple of reasons. One is it was a prototype, and second one is it was easy to sterilize because anything taken into an operating theatre has to be completely sterilized. And if you see the first picture, there is actually a student from Stanley who's standing behind the doctor holding the box. That is because we cannot have long cables, and the cables, they don't allow the doctor to move the hands freely. So that's what we did in the first prototype. So now and this is how we applied the sensor. That is, so you see a force sensor. This was not a great way to do it. So you see the sensor, we tape the sensor to the fingers of each doctor, and then the gloves are applied on top of it. And on the top photo, you can see the gloves that we made actually being used. And this is our current prototype. And we've turned that box into an arm-worn band, which is and with a small box which we made on our own board, which is also Arduino based still, but it has Bluetooth, and that's our board there, right there. And so here, this is currently under testing at Stanley, and it's been giving quite good results. I mean, there have already been, it has already been tested over 28 Whipple's operations, and it's given good results. So this is a quick video of how it works. That is a phantom, which is the doctor is operating on, and so he has to put the pressure, and the pressure is displayed here on the Raspberry Pi. So we were really excited after this project because this allowed us to do this very easily. I mean, such instruments are, the thing about open source hardware is it lets us do things for a lower cost, but the more important part is I think it lets us do things which are not possible before. There is no device that exists right now which can do this, and we are trying to come out with a device that can do this. So this is the first one. And this is something that is really exciting right now, transcranial direct current stimulation, TDCS. It's been a topic of a lot of controversy and debate and everything. So this is, but we've developed our own devices for TDCS. You might have heard about devices like Think and Focus and all that which work on TDCS. But we concentrated specifically on the treatment of schizophrenia. And this work was done along with another great doctor, Dr. Venkat at the National Institute of Mental Health and Neurosciences in India, NIMHANS for short. So quickly, what is schizophrenia? It's a neuropsychiatric disorder, which means that it's physiological, and it has a psychological part also to it. So if it's physiological, it has to be treated. And this is another statistics that I had to put in. It's ranked among the top 10 disabling disorders by World Health Organization, and it's quite common also. Symptoms are delusions, hallucinations, disorganized behavior, and progressive cognitive defects. Sometimes I think I have all of those. So I'm wondering, but in reality, if you go to the hospital ward, I've already actually been there so many times. It's really hard to see the patients because they're completely out of control, and that really makes my day. I mean, it tells me, okay, we are working in the right direction. So what is TDCS? Some of you might have heard about TDCS. It's applying a small amount of current, which is 1 to 2 milliamps. And in some cases, for some extreme conditions, we go up to 6 milliamps of current. And they are applied on the scalp using electrodes, conductive rubber electrodes, and they are dipped in a saline solution. And they are put in these two positions. That is the person you can see sitting next to me is Dr. Venkat. So the first trial was on him. So until we got ethics committee clearance for trying it out, we tried it out on all of us. And one more important thing that I forgot to mention was that the wireless EEG what we developed in the beginning was for predicting the occurrence of an epileptic seizure. So there are some prediction mechanisms available, so that's what we were working on. And the reason why we got into that is because I myself have epilepsy and it's quite close to me. So yeah, I'm in and out of psychiatrist's offices. So it's reported to have several therapeutic as well as non-therapeutic applications. Therapeutic is it can be used for, and that's pretty clear. I mean, it's used for mainly what this doctor is using it for is schizophrenia and extreme manic depression, which is really difficult to control. And the non-therapeutic, those are under that's under a lot of debate right now, and it's a very big source of controversy also in the medical field, and it's making a lot of news. They say that it can have cognitive enhancement as well as relaxation. In fact, the recent initiative, BRAIN initiative by President Obama's government, includes TDCS as a focus area. So we will just look quickly at how we use this in schizophrenia. When I say therapeutic, there is one more. There's still a lot. Huh? Okay, 5 more minutes. So TDCS, how it's being used, this is the most exciting part. I am going to run through this quite fast now because I don't have time. Treating hallucinations that are resistant to antipsychotic medications. So this was pretty exciting because what antipsychotics cannot do, TDCS was able to do. And the most common, I don't want to go into neuromodulation and neuroplasticity because we're running out of time. But what it requires is precision waveform generation of the current at the proper place. And the problem here was there are TDCS devices available, but they are not programmable to the right waveform, and they're just prohibitively too expensive. So this is the device that we made. It's also based on a SAM processor, and we made a display for controlling and monitoring the TDCS session. You can see the electrodes over there. This cost us less than $200 compared to another commercial system which was $7,000. I don't know why current control has to be so expensive, because if the electrical engineers over here would agree with me that current control is a basic electrical circuit. Quickly some experimental results. What we placed it in a place called the DLPFC, which is the prefrontal cortex. For testing the system, we tested out the cognitive capabilities of the system. So we had 2 electrodes placed in the 2 positions given there, and some tests were made, that is pre-TDCS and post session. So pre-TDCS, so the test is similar to a memory game that we play. It's called an N-back test. It's a sequence of numbers that appear on the screen, and the software called E prime is used, and then we measure how many numbers the person can remember, and the reaction time. So the 2 parameters here are reaction time and accuracy, how accurate and how fast react. So you can see some clear, this was data provided by NIMANS after the experiment. So you can see that there is a clear difference between before and after TDCS application. So this excited us even more, and we've now started exploring other aspects of neurostimulation like TFUS, which is focused ultrasound, which is really in the experimental stage, and also auditory neurostimulation. So what did we do even more? So we made a patient monitor. Patient monitors are pretty expensive. So what we did was we have made this hat, Healthy Pi, it's called Healthy Pi, for the Raspberry Pi. So we've got a Healthy Pi, we've got a Raspberry Pi, and we've got a display, and that's what I've got here. And I'm sorry, just. So what we aim to do there is it's a low-cost system, but still it provides diagnostic quality signals. That's most important, because there are a lot of off-label systems which are available, which provide mostly the false positives, false negatives, and all that stuff. So it's completely open source. You can't see the GitHub link over there, but it's open source. It's there on GitHub, and we've given instruction on Hackster. We use Hackster.io for our documentation. So here we just have a video of how it compares with a normal Welch-Allen patient monitor, and we got a very good correlation with that. And this is something this is the main application that we are looking at, which is telemedicine. How this can be used in remote villages, especially in India, who cannot afford a patient monitor. And we are not saying that this is a medical device. We are not FCC or FDA or anything certified, but something is better than nothing. So there's a live Plotly feed which is going on. So some of our contributions, TDCS, we are planning to open source it once the results are there. And open pressure is the first surgical tool that we spoke about. We've used it for other applications also, especially intracranial pressure monitoring. That is ICP, which is during neurosurgery. And I need to talk also about what could go wrong. And one thing is that you could. Okay, sorry. So just what can go wrong, because this is, I think it's very important. That's why I'm not skipping this slide out. Open source and medical don't go well together, because there are always medical standards to be followed and everything. And the misuse of TDCS is another very interesting thing, because if you don't know where to put the electrodes and you put it somewhere other than the extra encephalitis, that is other than the head, you could end up with even a cardiac arrest. So it's pretty powerful, but it's also, we'll have to do more, it has to be used responsibly. So other possibilities, false positives and false negatives, these are, I think, the material of which many lawsuits are made, and misdiagnosis. And so if the instruments are not calibrated properly, and if they're not used properly, for example, an electrode is not placed properly, then it could give false positives. So the point that I wanted to make is that we've used Raspberry Pi as our display. So this has become a new scientific instrument. So instead of spending $1 million buying a scientific instrument, we've used Raspberry Pi for all these three applications. So final slide. So open source hardware has allowed us to explore the unexplored. So it's not just about low cost, it's just that it's opened up new avenues. And we've handled important medical problems where it has definitely made a difference. And we also need to remember that more power, more responsibility. So I wanted to talk about the cycle again, and I put it in a cycle because the cycle goes on, and I'm still falling in love with so much open source hardware, and the journey will definitely continue. And some of the things that we're working on currently is NIR spectroscopy, and also functional NIR for brain mapping, and how to make those devices cheaper and more accessible. So I guess I'm out of time. I'm sorry to take too much time. Thank you.